Okay, cool. Thanks for having me. I'm Nils. I'm a machine learning research engineer at Pruna AI, where I mainly work on making this diffusers pipelines you already talked about a bit more efficient, faster. As you said, that's really a big topic right now. In this talk, I want to show you all the tools you kind of need to make your diffusion pipeline faster. Before we dive into the talk, I want to quickly explain what we as Pruna AI do, and maybe can go to the next slide. Yesterday, I randomly found this amazing talk by Björn Ommers, one of the persons behind Stable Diffusion. And this graphic really shows the problem that we try to solve with Pruna AI. So here you kind of see the compute of the frontier models over the last years. And if you look closely and see that the y-axis is logarithmic, you can really see that the compute grew really fast over the past years. And so the demand for compute is super high. And if you go once further, the supply in GPUs does not grow at the same rate. So GPUs also went fast over the past years, but not at the same speed as the demand grows. So there's this mismatch, and the question now is kind of how to solve it. I mean, one way of solving it, if you go to the next slide, as you might have known, is just like buy more GPUs to kind of satisfy your demand for compute. But personally, I don't really like that. I think it's not the most elegant solution. Just like throw compute and energy on the problem. So we at Pruna believe in a different solution, which you can see in the next slide, which is research. There has been a lot of efficiency research over the past years. Here I brought you a graph from the very cool Han lab that kind of shows the development of research papers in one really critical field of pruning. And as you can see, like the research hasn't slipped on like making these models more efficient. However, I think there's still sometimes a mismatch because there is really great research on making these big models more efficient, run faster, with less operations. But oftentimes the problem is that researchers don't really have the time to kind of make their code production ready and stuff like this. And that's kind of where Pruna AI, like the company I work for, comes in. And if you can go to the next slide. So we kind of published at the beginning of the last year a open source repository where we we kind of make it easy to use many different algorithms from research and especially make it easy to combine them. And in this talk today, I will show you kind of how to do it. Everything is, we have like an Apache 2.0 license, so it's really open source. You can play around with it. And if you can go to the next slide. Today, I want to show you how you can kind of use our package, which also works for example, transformers and the transformers library, how you can kind of use this for the diffusers library. And here you kind of see a rough overview of over the algorithms you have. You don't have to understand them right now. I think we will get into it. So yeah, to make it a bit more concrete, I think it makes most sense to kind of select one model that we want to like make as fast as possible in this talk. And as the model, I selected FluxDev, which you see in the next slide. It's a pretty obvious choice to choose because I think it's the second most liked model on Hugging Face. Also, it's a frontier AI model from Germany, which is kind of rare. I really like that. And as you can see, like the images it's able to produce, they look really crisp, really nice. I think the only drawback is that it can take some time to get these images. It's a really big model, which also means it's oftentimes very slow. And on the next slide, you can see kind of a analysis from this company called Artificial Analysis that kind of looked at different providers that kind of serve this model over an API, and they kind of measure how long a generation takes with different providers. And as you can see, generating only one image with the standard settings takes between 3 and 9 seconds. That's, I think, quite much, considering that most of them probably use like really state-of-the-art hardware to serve these models. In particular, if you go to the next slide, maybe we can make it that I can just I type something in the chat and maybe then you can switch. I think that's maybe easier than always saying that. I will just type some words in it. So yeah, basically here you can see that kind of did some benchmarking over the past weeks and found out that actually most of the fastest providers so far, they already use these optimization techniques that we will also see today. And yeah, I think as the objective for this talk, let's see how fast we can make it, if we kind of where we land in the end with our open source solution. And yeah, I have to say, I start with a slight disadvantage. Relatively to some of these API providers, I'm GPU poor. I only in parentheses work on a L40S GPU. So for me, if I take the model as it is from the diffusers library and generate one image, it takes me roughly 16 seconds, whereas for a H100, it only takes 6.5 seconds. So if we go back to the this graph, that puts me at last place, and it's not even close. Yeah, but hopefully we can change that. So before we dive into how we can optimize it, I will give you a quick overview of how these diffusion pipelines and in particular Flux works. So usually what these pipelines do is they start with a random image at the beginning, right? As you can see here on the top left. And then usually you have a very huge neural network. In this case, it's a transformer for Flux that you kind of use. You feed in like this random image to this transformer, and then this transformer has kind of learned to denoise this image. So it will remove some of the noise. So it will give you a less blurry version of that image. And you not only do that once, you do it a couple of times. So yeah. You do it like many steps. You kind of repeat this process of calling the transformer. And I think for Flux, it's in total it's 28 steps. You kind of like throw your transformer at an input, update this input slightly, use this new input, use the transformer again. I guess you get the idea. So now we can think, okay, how can we make this faster? Because as you can imagine, like calling this huge transformer 28 times is quite slow, and it's like really the reason why it takes so long to generate an image. And one thing that you can maybe also see on the left is, right, basically what we do is we consider like 2 consecutive steps. We only change the image that we feed into the transformer slightly. So actually it kind of is intuitive, makes sense that kind of what goes on into this transformer, think of the attention layers and so on, is also very similar from one step to the next step. And that's exactly the idea so-called cachers try to make use of. So the idea is kind of that basically these computations in 2 consecutive steps of the transformer are very similar. So you can kind of get away by caching them and then reusing them a couple of times. You can also see this on the slide on the right-hand side. So how basically Flux with caching would work is at the first step, you would use your transformer as you would normally do, but basically for all the heavy computations you do in the transformer, you would kind of save them somewhere. And then in the next step, instead of like performing all of these heavy computations again, you just use the cached values, which are like probably very similar to what you would have computed with the updated input. And that's basically like the main idea behind caching for diffusers. At Pruna, we currently support 3 different caching algorithms for Flux. We have our proprietary, or like our own implementation of the Fora paper, and then we also support the 2 cachers from Hugging Face, PUB and FasterCache. And to give you an idea of how basically caching affects the output, here on the left you see basically the output of the base model. Yeah, it takes 16 seconds, as you can see, and it's a really cute, nice, round knitted prune. So let's see what happens if we apply very mild caching to it. So here you can see we use a cache interval of 2, which kind of means we compute the transformer once, and then for the next step, we would reuse all of the cached values before we would like compute the full transformer pass again. And basically, as you can see, the image basically doesn't change. I think the cheeks slightly change, but overall, I think it's still a nice image. And of course, you can go even more aggressive. of course, at some point you will see some image degradation. And maybe if you don't see it here, it becomes clear when you kind of zoom in. So for example, here I would say like, so the first two steps with caching, I think it looks nice. I mean, you have like this heart cheeks, which I really like. But then like if you go really aggressive, you go down to like interval equal to 4 on the right-hand side. You can really see you kind of lose the eyelashes, and also like the cheeks are not the heart anymore. It's just like some blurry ball-ish thing. And yeah. While I like looking at images, we also try to be a bit more subjective about this. So what I did is I did not only consider this one prompted image. I looked at a couple of images. I looked at 200 prompts from the Drawbench benchmark and computed some metrics on them. So on the left-hand side, what I kind of display is the ANI QA, which I plot against the latency. And ANI QA is one of these quality metrics that claim that they kind of align very much with human preference. So a high score kind of means that most likely humans would like the image. And on the right-hand side, we also have a complementary metric. It's called fidelity. What it does is basically it takes the output of the base model where you don't apply any optimization, and then kind of compare to the images that get generated by like the optimized versions. And then you kind of compare them and see, okay, how different are they? And here I would say also higher is better, and everything above, I think 0.9 is pretty much the same as the base model. And then I think everything above 0.8 is still pretty good. So maybe then minor details, as we saw with the cheek, can change if it's above 0.8. But still like a good value. And so let's see where our 3 different caching methods land according to these metrics. So what you can see in gray and purple is that the both caching methods from Hugging Face, they are really similar to each other, I think, at least regarding these metrics. And also they yield a higher fidelity to the base model, which is really nice, which you can see on the right-hand side. But the Fora cacher actually is like the fastest one of them, as you can see here. And one thing that you also can see here in this chart is basically because these different dots kind of represent different configurations. And so kind of the idea here you can see is like at the beginning when you start caching lightly, you still have like a similar quality to the base image and the base model, but then at some point, as we saw, like with interval equal 4 on the last slide, the quality really drops off. So yeah, basically it kind of also shows you can't do this like super aggressively. Nice. Okay, so now we learned about one way of making a pipeline faster. And conceptually, what caching does is kind of it produces like these expensive operations that we do within the transformer, right? So another way that's kind of orthogonal to that is that we can also maybe try, instead of like reducing the number of operations we do, we can also try to take the operations we still have to do and make them faster. And I will present you 2 techniques that do that. But before we can dive in, I will go on a quick detour where I explain how GPUs work, at least on a very high level. So for the next 5 minutes, let us think in this metaphor of thinking of a GPU as a factory. Let's make this a bit more clear. Okay, so maybe let's look at the different stacks of a GPU, right? So probably the most important stack of a GPU is its GPU memory. In my case, on my machine, I have 48 gigabytes of memory. And you can think of this GPU memory more or less as like the size of your warehouse. So in my case, my warehouse is super big, right? But by loading your model to GPU, you basically just store all of the numbers, the weights and biases that make up the model in your warehouse. So by itself, that does nothing, right? And the magic really happens when you do some linear algebra with these weights and biases. So we have to kind of move these numbers, these weights, these biases to our factory. And for this, what's really important is the memory bandwidth. In my case, I think it's 800 something gigabytes per second, and it kind of tells you how fast you can move your weights and biases to your GPU back and forth. And that's really important because actually, on the last image, the factory was huge, but in real life, the factory, like your GPU cores or whatnot, you can think of it as being very, very small. So, for example, everything that wants to go to your GPU cores has to go to your L2 cache, which is only 48 megabytes big in my case. So basically, you can't just go ahead and like load it or bring all your weights and biases to the factory at once and then do all of the computations there. You rather have to move around the different things that make up your transformer, for example, one by one, and do the computations. And the key number here that kind of specifies how fast your factory is the number of flops you can do. In my case, since Flux is in BF16, this number is, I think, 360 teraflops. Okay, nice. So let's think about what could be potential bottlenecks of all of this. So one potential bottleneck that could kind of hinder the production of our factory, of our GPU, is kind of that we are compute bound, which kind of means that maybe we are super fast at supplying the factory with weights, biases, but we're just not fast enough in doing like these computations, right? That could be one bottleneck. And actually, the more likely bottleneck when doing inference, as we do, is that we are memory bound. When we are memory bound, it kind of means that like our memory bandwidth is the problem. So our factory maybe is fast enough, right? But we're just not fast enough at supplying it with weights and biases to do the computations with. And let me first start by explaining one way of kind of tackling this memory bandwidth problem. So let's stick with this very simple example you see on the right. So let's assume we want to perform this computation. So we have like input X, and then we want to perform a linear layer followed by a norm layer to get an output Y. If I would have coded up this whole thing in PyTorch and performed it on my GPU, what would happen is my GPU would sequentially perform these operations. So how this would look like is the following way, right? So at the beginning, we first have to do the linear operation. So you shift like basically your input and your linear layer to the GPU. Then on the GPU, on your factory, you do the operation, get some intermediate result C, and then you have to bring that back to your warehouse where you basically need to take and grab your parameters of your norm layer, bring that to the factory again, do the last part of the computation, and then you're kind of finished. And as you might think, if we're memory bound, if really the problem for us is that we're not really that like the speed at which we can shift around things is the problem, then like doing so many shifts that kind of feel unnecessary seems a bit like a problem. And that's exactly what Operation Fusing tackles. So there's a really nice solution to that. And basically it is, if you write a custom kernel, and kernel in the context of GPUs means some custom code that, for example, implements this operation we want to do. If you write this custom code, that kind of allows you to kind of bring all of the ingredients all together to the factory, make the computation all at once, and then bring it back, right? So that's how it looks. You can, if you have a kernel for this operation, you kind of bring the norm, the linear layer, and the input to the factory, then do the computation there, and then you're kind of done and can like bring back the final result to your warehouse. Nice. Problem is actually writing CUDA kernels is not super simple. I tried it once. Trust me, it's very difficult. If you can do it, it's like a really valuable skill. Many people want to have the skill, but I don't have it. So how can we make use of it? And the cool thing is you might have already used it, right, without knowing it, because that's basically what Torch Compile does. So Torch Compile, basically what it does is it takes, for example, if I apply Torch Compile to the transformer of my Flux model, it would kind of analyze the computations I do in the transformer and then already check, okay, maybe I can fuse these two operations together. Maybe I have already like a kernel lying somewhere around that kind of fuses these operations I see here in your transformer together. And that's really magical, right? It does all of it for you, right? It checks all of the computations you do and already like fuses stuff together, which is really cool. In Pruna, we don't only have Torch Compile, we also have Stable Fast as a compiler. It's just a different way of doing it. I think Stable Fast works very well for stable diffusion pipelines. And yeah, so let's see how applying Torch Compile and Stable Fast on top of this Fora cache affects our output. So in orange, you see kind of what we had at the end of the last step, when we had like the cachers, right? The yellow line is basically just the for cacher line, and then the green and red lines are basically what happens when we add stable fast and torch compile to the mix. And as you can see, basically the graph just is shifted to the left, which is super nice for us, because it means kind of that the quality stays unchanged, as you would assume, because you still do the same operations, right? But you can just do it much, much faster. So it's basically free lunch, which you always want to kind of take if you can. And in this case, and that also can change from model to model, torch compile works a bit better than stable fast. So basically free lunch, I mean, the only price to pay is that at the first iteration, torch compile can take a while. It needs to analyze your compute graph, look for kernels. That can take a while, especially for big models. So for example, for my big transformer of the Flux model, it takes 1.5 minutes. But there's one trick we kind of implemented, is that basically what you can do instead is you can just try to compile the blocks that make up the transformer instead. And this is much, much faster. It only takes 50 seconds. And for some reason, also stable fast is faster when it comes to this warm-up compile time, basically. Nice. So now we have already caching and compilation. So, and as I said, like this compilation and operation fusing helps you when you have like this memory bandwidth problem. But for example, if we are actually compute bound, which is actually reasonable because the Flux model, as I said, is like super huge. It's like a transformer with a super big sequence length. So we're actually, to some part, also compute bound. So what can we do against that? So from what I said so far, it seems like we can't change much about it, right? I mean, my GPU just has this amount of flops it has, and I can't really do much about it. But there's like one detail I kind of spared out on, which is that the amount of flops, at least for the newer GPUs that your GPU has, depends on the data type you do the operations in. So for example, I had like 300 something flops when doing bfloat 16 operations. But if I, for example, switch down to a less precise representation of my numbers, so if I use, for example, a int 8, I only would use 8 bits instead of bf16, then this allows me to kind of do more operations per second. Actually, almost double the amount of operations per second, which is pretty cool. That's something we can do to tackle the compute problem, and it has also a side effect. So basically, if we kind of use only 8 bits to represent all of the weights, all of the activations that happen in our transformer, then it also kind of means that the size of them halves, basically. So this also makes it possible to kind of shift around things much, much faster from our warehouse to our factory, because everything is just half the size if we, for example, go down from bf16 to int 8. Okay. In Pruna, there is only one quantizer that supports this type of quantization I just described, this dynamic quantization, where you actually perform the computation in this lower precision format, which is torch.io. And let's see what happens to the output if we add this quantization to the mix. And unfortunately, as you can see, if we apply it naively, it kind of destroys the image. It gets a bit more blurry, the image. Again, like the cheek turns from a nice heart to like a fuzzy thing, right? So it's not super nice. And it's also a bit blurrier, I would say, the image. So that's not super nice. I mean, but you also like get a bit faster. So maybe that's the price we have to pay. But that doesn't have to be the case. At least for Flux, it doesn't have to be that way, because basically what we did in the past step, that's also something you do, like when you naively just throw a quantizer at a transformer, right? You quantize everything. So for example, you would also quantize embedding layers and normalization layers that actually are not super compute heavy. They don't really contribute much to your overall inference time, but they are somehow super sensitive to quantization. So actually what you want to do is kind of only quantize like these huge, big attention and linear layers that actually contribute to the compute time and only quantize them. And then you do that, as you can see on the next slide. You can see that the quality gets much better. And actually, if you look at the time on top, the time stays roughly the same, right? Because we can still like quantize all of the expensive operations, but just spare out on these norm computations and so on, which is, I think, quite nice. We can also see this in our plots, right? So orange line was where we left at the last slide. And now you can see here, basically in beige, you can see what happens when we apply quantization naively. And you can really see this drop in performance in terms of quality and also fidelity. But as I said, if we do it smartly, you can see here in purple and in pink, basically the quality and the fidelity stay roughly the same as to the combination of Fora and Torch compile, which is, I think, quite nice. So it's also kind of free lunch, I would say. Nice. So I think now we combined caching, we combined Torch compile, and we combined quantization. And these are our final results, right? We started with roughly 16 seconds, and depending on how aggressive we go with the caching, we either end up with 5 seconds or 3.7 something seconds, which is, I think, pretty amazing, because the image to my old eyes still looks quite the same, right? And also, if we go back to this benchmark I showed at the beginning, right? If you remember, we started at the back, right, at the clear last place, and now it brings us at the second place. And I mean, the cool thing is, right, we still use my not so state of the art GPU and still can compete with all of these super big inference providers, which is, I think, nice. And one aspect of it, so far I didn't show you any code, right? I was just talking about the concepts and so on. And I think here you can kind of see the beauty of our open source repository, which is that kind of it makes it super easy to combine and apply these methods. So all I described up until now, so basically the code that produced these results, you kind of see here. It's like 10 lines of code. You just install Pruna, basically, and then it's these 10 lines of code where you kind of just specify what you want. Okay, you want, as a cache, you want to use Fora, for example, then you use the interval 2 or 3. Then you say, okay, as a compiler, use Torch compile, as a quantizer, Torch AO. And you can also specify this one option I mentioned that allows you to not quantize your norm and embedding layers. And then you basically have the same results as I have, this nice 4.2x speed up for Flux. And of course, and probably because Flux is like a super big model, you might not be able to run it on your gaming GPU, but basically you can use the same formula that I kind of presented also for different types of models. So for example, for the stable diffusion models that are usually much smaller than the Flux model, for them, you would like to use a different combination. I think for them, the cache you want to use is deep cache combined with stable fast and a QKV factorizer. And then the results are quite similar. So here, for example, I have some results for the SDXL model. So basically, if you just take the base model on my machine, it takes roughly 6 seconds. And then if you use this combination, depending on, again, how greedy you want to apply caching to it, you can go down to 1.5 seconds, which is, I think, also really nice. Let's wrap it up. At the beginning, I kind of showed you how to combine different algorithms, or that we kind of think at Pruna think that combining different sorts of algorithms gives the best results. Then we kind of looked at caching and basically found out that caching, what it does is just it reduces the numbers of operations you have to do, which kind of lead to a speed up. And then we went to this factory GPU metaphor, and with that metaphor, I kind of explained to you how compilation, but also quantization works and why it works. And all of this together basically gives this nice 4.2x speed up for Flux. At basically no quality degradation. And that's it. If you have any questions, feel free to ask in the chat, or I don't know if you can also come to the stage and talk with me. Thanks for your attention, and it was a pleasure to be here.
Really nice. I focus a bit on reading the Ds and clicking, but I think I also listened. I think I learned quite a bit. Anyway, because as I said before, right, I haven't followed everything like over the past year or so, and then just getting your really visual presentation about things, how it all works together, and like what's there. That was really interesting. Yeah.
Cool. Nice to hear. I have to agree. I think like I just started like with this stuff like this year, and it's a lot to learn, right? Because this diffusers library is super huge. I mean, there's a lot of cool stuff going on left and right, and sometimes also really hard to kind of keep an overview.
Yeah, absolutely. Yeah. Are there questions? I think I can just share your slides together with mine afterwards, right? Because now I have them. Anyway.
Yes.
So I will just post that.
Perfect.
Yeah. I will also post the recording, as I said, probably next week on LinkedIn sometime. Yeah. Maybe I have one more question about Pruna, because I never heard about it before, actually. So maybe I can quickly tell a story how I connected with Nils. It was more about someone who worked for Hugging Face, who I asked if he wants to talk here, but he said, he has no time. But he's now working for Pruna and another company as basically what you call it, developer relations person, right? Developer person. And so he connected me with Nils. And yeah, it's really cool to see, as a German myself, right? I'm always happy about European or even German companies, startups. And I think you're located in Munich and Paris or something?
Yes. Yeah, so part of our founders are from Germany, and part of them are from France. But so basically all of this like came to be like from, I think one of our co-founders is Stefan Günnemann. He's a professor at TUM, and basically I think out of his research chair this whole thing started. And yeah.
I see. It's cool to see stuff coming out of research and going into the real world, right? Because that's the main problem of research, as you said before, right? There's a lot of great research doing stuff, but most of it is just for conferences and then it disappears. But it's great when people pick it up.
Yeah, it's actually, I think sometimes it's surprising how much good stuff you find, but it's just like right now, I mean, such an overload of papers and ideas and sometimes I think really cool stuff gets lost. I think, for example, one method we currently also use in our Pro version, it's like something probably most people never heard of it, but it works super well, but somehow nobody knows about it. I don't know. And yeah.
Oh, Lane knows you already.
Oh, that's cool. Cool, yeah.
See, Lane is one of the regulars here on Discord, and he's also part of the Hugging Face Fellows, which I'm also part of, right? Yeah, it's great, Lane. You're well informed, as always. Okay, if there are no more questions, I think we'll go on to the quiz. And I mean, whoever wants to leave can leave. Whoever wants to participate and watch, yeah. Thank you again, Nils. I will move you away to the audience. Sorry, now you could have said something. Yeah. Anyway, okay, let me get to the quiz.